Okay, hello everybody. I was asked to talk about black hole Xray binaries, and of course the topic is very broad, so it's very difficult to cover all the aspects of this field. And I will also actually just try to cover the work that my group in Turku has been doing. And this is high precision optical polarimetry and what we can learn about orientation of black hole Xray binaries on the sky and whether we can get the clues about nature of optical emission from polarimetry. So I will start with motivation, and then I will skip all the previous detections, polarimetric observations of black hole Xray binaries, and I will jump directly to the work that we have been doing during the last 4 years. Black hole Xray binaries, obviously black holes that are accreting gas from their companions and the bright X-ray objects. Most of those objects that we know, they are in low mass X-ray binaries. So it means that they have low mass companion and they are transients. Therefore, they don't shine all the time. And it's interesting actually to see those objects at different luminosity stages so that we can actually observe this object that they go through different states and their spectra changes from all the spectra, like from radio to optical, X-ray domain, all of them are variable. And so some of the unsolved problems for today's talks are the nature of the optical emission from these objects and whether we can actually get a clue about the black hole spin and orbital spin alignment or misalignment in these objects, because so these are the questions actually that we would like to answer, and the polarization will hopefully provide us with the clue to answer those questions. In the picture that you see here, this is a sort of an artist impression, and Rob Heinz is an artist here. How the black holes look like when you have an accretion disk around the black hole. And there are a number of components that contribute to the observed spectrum. There is an accretion disk itself, which outer part emits from the radio, from the infrared to the optical. The inner parts, which sometimes are we call hot flow, so they produce hot X-rays. And there could be also disk wind, and there is a jet also that at least seen from radio to sub-millimeter domain and even into the infrared. And you can have a companion star. So even if X-rays are normally people believe are produced in the central region around the black hole, the optical emission can be produced in any of these by any of those components. And we start from V404 Cygni, which is one of the famous black hole transient. It was discovered a long time ago as an optical nova, and it was went in the outburst and seen with X-ray instruments some more than 30 years ago. And recently, in 2015, it went to another outburst that was, of course, it was very bright X-ray source, and people jumped from basically from radio to the gamma rays. Everybody observed the source for as many as they could, but the outburst was quite short. As you see here, this is the optical light curve. Basically, it was the object died within a month. Normally, the outbursts last much longer. On this upper panels, you see polarization in 3 different filters, B, V, and R, and the polarization angle. And what we have observed this object with the dipole 2. Dipole 2 was introduced yesterday by Andrei Berdugan at the 60 centimeter KVA telescope at La Palma. And after a while, when the source dimmed and went to the quiescent, we observed it with a bigger telescope, 4.2 meter Wilhelm Herschel telescope, with the same instrument. And we see that there is some variability here certainly in the B band. What we have noticed that actually the polarization this is on the UQ plane, the polarization changed from the outburst to the quiescent. So there is very significant changes. So obviously in the quiescent, so there is some intrinsic polarization related to the object. It's not only of interstellar origin, but if you look at the field stars, you see that, of course, most of this polarization, unfortunately, is of interstellar region. And the polarization angle of nearby stars is very much consistent with the polarization angle that we see from the object itself. And if you look, there is actually very nearby companion, 1.4 arc-second away, that you can observe with Wilhelm Herschel. It has exactly the same polarization in quiescent when the object was in the quiescent state. But it means that in the outburst there is some intrinsic polarization, but it's quite small. It's about 1%. So we can now look at this field stars. We can look at the companion which is nearby, and we can subtract. We can estimate interstellar polarization very accurately, and therefore we can subtract it from the observed data. And we see now that this is intrinsic polarization, that it has very weird dependence on the wavelengths. It's sort of, there is a B, it's not clear, there is a big error bar, because actually it's very weakened B band. But the polarization drops towards R by a factor of 2 from V to R. So that tells you at least that's probably not related to the jet, which is normally has very red spectrum. What was also interesting, that polarization angle was variable between -30 and 0 degrees. But interestingly, this polarization angle was consistent with position angles of ejections observed with BLBI in the radio, the paper published a couple of years ago. And so here you see it also from -30 to 0, which is really a very interesting coincidence, if it's coincidence. But probably it's not. But if it's not the jet, judging from the spectral shape, but it is very consistent with the position angle of the jet, then what it is. So it could be that because this source was very bright, it was accreting at super Eddington rates. So therefore, one expects that there is a huge envelope around the central object because the accretion disk is it has very high luminosity, so it produces wind. And so this polarization probably is produced in the wind. So, and this wind probably somehow collimates the jet in the end. So there is a relation between the wind, the symmetry axis of the wind, and the jet. And the wavelength dependence in this object is very much similar to what one sees, one have seen already a long time ago from B stars. So this is, for example, from the old papers by Pockert from '79. And this is explanation for this wavelength dependence. Basically, it's very simple explanation, just because in B stars, the ratio of the opacity to the scattering is changing. It's a wavelength dependence, and therefore one gets immediately that polarization also will be wavelength dependent. And so this is consistent with the data. Then the second object that I will have time to talk about, it's Maxi 1820 plus 070. This is an interesting object that went at outburst 3 years ago. Now, it's a lot of information here on the first slide that probably we will not have time to read everything. What's interesting that we actually know a lot about this object. We know that there is a radio jet, an X-ray jet. There is a position angle on the sky about 25 degrees. We know the distance from radio parallaxes. We know the inclination of the jet from the superluminal motion. We know the orbit inclination from the ellipsoidal variations. And we know a lot of things. What we don't know orientation of the object on the sky, of the orbit on the sky. We know the jet, but there is no orientation of the orbit. So which would be of interest. In the outburst, we have a lot of data in these different colored regions. So basically, we observe it every night. And what's interesting, that's so there is hot state in the beginning of the outburst when the X-ray spectrum was hot. There is a soft state when there was slightly, the object was bright in the X-rays, and there is what we call decaying hot state when the object was basically dying out. We had also a number of observations here. So this during the outburst, we see clearly different polarization that was variable. But before we know what is the intrinsic polarization, again, we will have to be careful, and we'll have to subtract the interstellar polarization. From the map here, you can immediately see that the nearby stars have a position angle of polarization slightly different from what we see from our object. And so, here is polarization as a function of parallax. We can see that actually polarization depends on the parallax somehow, but not very much. and this different colors. This is our object, the different stages. So actually, again, we go and take the object, take the stars which are at similar distances, and estimate the average interstellar polarization towards star, and we can subtract from the data. So we have here a collection of observed polarization, interstellar estimation, and then the intrinsic polarization. What's interesting here, I put in these red boxes, is the position angle of the polarization angle during the hot state. And what you see here, it's about 20-25 degrees, which is exactly what we have seen in the, there is a jet here, image from the X-ray, in the X-rays, one sees from the jet. So again, there is some correspondence between what we see in the optical position angle of polarization and the position angle of the jet. Very nice coincidence. So in the hot state, the polarization was about 0.5%. In the soft state, which shown here with these boxes or squares, the polarization was very low. It was about 0.2%, and it has different position angle. So interesting. So you clearly see what one sees that there is in B band. Clearly, one sees that there is additional contribution to the polarization because the points here are not aligned with the points in the V and R band. Basically, it means that in the B band there are a number of components contributing. And in the V and R is probably this non-thermal component that is dominated. And in the B band, we expect there is accretion disk also emission that's contributing. So therefore, there is a difference. But what we actually see that in the soft state, when we know that the emission mostly in optical dominated by the accretion disk, the position angle is very different. It's minus 16 degrees here. So there is, it means that actually in the hot state, somehow polarization knows about the jet. In the soft state, it probably tells you about the accretion disk. So there is clearly a huge difference in the position angle. So this was in the outburst. And then we go to the quiescence. And in the quiescence, we observed the source 3 times, 3 different occasions. First time when the dipole UF was installed at the Nordical Optical Telescope in July 2019, then we observed again in April 2020, and then the last time in July 2020. Actually, we observed a number of other times, but the source wasn't really in the quiescent state, but probably some failed outburst. And the station is very much different. Now we see that polarization degree is just a factor of 10 larger. Now it's 5% in the B band and about 1 or 2% in the R band and somewhere in between in the V. So it's the polarization degree has a very blue spectrum. It's variable, no orbital variations, obvious orbital variations. There is some, but you know it could be some stochastic variations. Position angle I didn't plot here. I blocked so that we will not be spoiled when our paper comes. That's when the paper comes out. So this will be submitted within a week to some interesting journal. And but it's very different from what you see in the hot state. More consistent to what we see in the soft state. So the picture now of the black hole is probably like that. You have an accretion disk and the jet, which is pointing sideways, sort of. So there is a huge misalignment between the accretion disk axis and the jet axis, which is probably related to the black hole spin axis. So the final thing that I would like to talk about is the spectral energy distribution that we observed from this object in the quiescent, which is really amazing, I think. This is the radian corrected spectrum collected on the Liverpool telescope together with the Swift UWatt space telescope. And what you see here, there is UV excess. So, I mean, it's not obvious in this data, but actually there is strong excess. So one can fit the low energy data with some accretion disk spectrum with the temperature about 6,000 degrees. But there is an additional component here in the blue, in the UV, basically peaking at the UV. What's also interesting that with blue here triangles, I plotted the polarized flux. So what I have done is I multiplied the observed polarization degree with the observed flux, and then I plotted that. I also scaled it a little bit, and what's interesting that this shape of the polarized flux is very hard. That it's consistent with being like continuation of this UV excess to the low energy. So when we fitted the data, we actually fitted this broadband spectrum together with this polarized flux, which was fitted just by this additional component, which here is fitted with the black body. And also the star contribution from the star, which is basically a black body with 4,500 degrees, was also, there's like 20% contribution from the star to the spectrum. And that most of the emission is produced by the accretion disk. So the question is now, what is this polarized component and why it's polarized at the level of 6–7%? Because we see it, at least in the B band, it's already 5% polarized, but there is dilution from this component here. So at high energy, it can be even higher, 6–7%, maybe even 8%. Okay, so the question is, what is the nature of this polarized excess? And first, of course, the question whether this excess is real. The only other object that showed such an excess was another famous black hole transient, AO 620-00, which was in the outburst long time ago, in the end of 70s. And people have observed these objects in the quiescence many, many times. And one of the observations was done by with HST, and this is with other instruments too, but important are data from HST published by Freund in 2011. And here we have new spectrum in the inset. You see that there is a clearly, it seems that there is a disk component going down, and there is the UV excess. So clearly we see the UV excess. There is no much discussion where it's coming from in this object, but we clearly see that there. So we at least there is another object which showed this UV excess clearly. So I believe this is excess is physical, so it's real. And then the question is, what is that? So the first thing that came to our mind is that you have, in addition to the cold accretion disk, you have some hot matter, because you see some X-ray emission also, very weak, but there's still some X-ray emission. So the accretion in this quiescent state, which is actually not very much quiescent, or it is quiescent, but it's not completely that object, right? So accretion still goes on. So there is some X-ray emitting region. And it means that there is some hot gas around the black hole somewhere. So the famous model for this region is called ADAF, advection-dominated accretion flow. So you have a cold accretion disk, and the inner part of the flow is hot, is puffed up. So what we did, we just made very simple simulations if you have just photons from the cold accretion disk injected in this hot flow. So, and then we can just compute what will be the polarization degree. And it turns out that you can produce in this geometry polarization degree of the order of 5 to 10% easily if you observe an object at inclination between, let's say, 60 and 90 degrees. And the object, this object is observed, we believe, at least if one believes Manuel Torres, at somewhere 70–75 degrees, probably, ±5. Okay, so this is reasonable. We can produce this polarized component with a polarization degree of order of 10% easily. And so here, this is the simulation that we did. We have black body spectrum from the disk. And then here, the red is just single scattering in this ADAF. And the blue curve here is the polarized flux. So basically, this polarization degree multiplied by the flux, which, of course, at low energies, they look very similar. As you see, polarization degree is very constant with wavelengths. So at least this model explains the wavelength dependence of polarization. It explains the degree of polarization, and actually then we also understand where this UV component comes from. Okay, so
2 more minutes.
The following here, I will maybe now summarize what has been said. So we have with 2 high precision optical perimeters, we observed 2 black hole transients. And we observed them both in outburst as well as in the quiescence. We see variations of the polarization. We have observed also a number of field stars and accurately determined interstellar contribution to this polarization. What's important, probably I should have mentioned it, that in many of these observations, the effect that we see is just a very small fraction of a percent. So, for example, in the soft state of Maxi 1820, the polarization degree is 0.2%, but it's highly significant. Okay, so it's with the polarimeter that we have in hand, we can detect that. But of course, if you have accuracy about 0.1%, that's impossible. Our typical accuracy can be 10 times better, 10 to minus 2%. So in the VF4 of Cygni, which was a super-Heraklion source, we see polarization above 1%, rising towards V band. We think that it's produced in the optically thin envelope. The polarization angle is very similar to what you see with the jet position angle. So probably the jet and this wind know about each other. Maxi 1820 in the outburst shows zero polarization decay in hot state, which I forgot to mention actually. And actually what's interesting that in this moment there was no winds, but in the rising hot state there were winds. So therefore we believe that this polarization, which was about 0.5% in the hot state, is related somehow to the wind, because we see that in similar states the polarization is different depending on the whether there is wind or not. What's interesting that in the polarization angle is 25 degrees, so it's basically the polarization. The electric vector is parallel to the jet, even if it's produced by the wind. So again, somehow the wind and the jet know about each other. But in the soft state, the polarization angle is very different, because the B band, the radiation is probably produced in the disk. In the quiescent state, Max 1820 produce very much higher polarization. Position angle is very different from what you see in the hot state. It's very different from the jet position angle, which translates to the high misalignment between the jet, which means black hole, and the disk axis. So which is very interesting in itself. And so in the data that we got and see the polarization flux, the explanation for this polarization flux and the presence of the UV excess probably tells us that the explanation for this data is that you have some scattering of the disk radiation in some hot flow, which people knew that it's probably there, but now we have actually interesting evidence, completely unexpected evidence for this flow acting in the near quiescent state. And I'm done. Thank you very much.